Hi everyone, I am Wan Zhengzhu from University of Illinois at Urbana-Champaign. I am thrilled to be here to present our work, Self-Supervised Euphemism Detection and Identification for Content Moderation. This work is done by myself, Hong Yugong, Rohan Benzo, Zachary Weinberg, Nicola Christine, Julia Fenty, and Suma Bhatt. It is a collaborated work with University of Illinois at Urbana-Champaign, Facebook, Carnegie Mellon University, and University of Massachusetts at Merced. At the era of big data, people make a growing amount of social media posts every day. Therefore, it is critical to ensure that the cyber environment is safe and healthy. One important task here is content moderation, which is to prevent conversations which are inappropriate on the social media platforms. When a post on the social media platforms violates rules and regulations or contains illegal content, human moderators or automatic moderation could easily catch them and block the message. However, individuals and groups have a long history of using code names or euphemisms to conceal what they are discussing in order to evade the content moderation. For example, when they replace the drug cocaine to coke, replace the pistol gun to gets, replace the prostitute to the girlfriend experience, and therefore they will usually evade the content moderation. Existing tools typically make use of a banned list, but they are notoriously imprecise. One reason is that when a euphemism is banned, the group could simply invent another one. That would leave the content moderator one step behind. The table here shows some involving euphemisms for some sensitive contexts. Our work is to automatically detect and identify the euphemisms, which facilitates content moderation. More formally, we define the problem into two stages. One stage is euphemism detection, and the other stage is euphemism identification. Euphemism detection is to detect all the codenames or euphemisms that are used to replace the target keywords. For example, in the context of drug, people often use the code word like weed, coke, blueberry, and so on to refer to some drugs like marijuana, cocaine, and so on. So the problem is that, can we detect more euphemisms like those from the text corpus alone? Note that we expect the input to be only two information. One is the raw text corpus, where you would like to extract the euphemisms from. One example is the social media post. The other part of information is your interested target keywords list. So the other stage is the euphemism identification, which is to identify what a euphemism refers to exactly. Give an example euphemism. Give a euphemism weed. We would like to know that it refers to marijuana. Give another example euphemism of coke. We would like to know that it refers to cocaine but not something else. So the output from an algorithm is typically a probability distribution, where we would prefer to see the probability of marijuana is the highest, given the euphemism weed. Again, we expect no additional information or resources required, but only the text corpus and the euphemism. Now let us look into the first task, which is euphemism detection. So first, let us see how previous work have achieved on the euphemism detection. So first, we find almost all existing work require additional information as input, which is marked on the left. For example, they may require a dark corpus where only euphemisms are used, or they may require some additional human effort. However, such additional resources are very costly to obtain and are not often available. Instead, we would like to propose a model that requires no additional resources. On the other hand, in terms of the NLP techniques shown on the right, most existing work utilize the static word embedding. In particular, they use word-to-vec to detect the euphemisms. However, they fail to conquer the most important challenge of the task, as I will show later. So we resort to a newer class of embedding, which is contextualized embedding, learned in the BERT model. And we explicitly separate those contexts and make use of the context. So compared with the prior work and our goal, the task of euphemism detection has three main challenges. So first, how can we make use of no additional resources at all, unlike all prior works? Second, how do we deal with these noisy contexts on the euphemisms? So how do we deal with those contexts on both the euphemisms and the target keywords? So the noisy context on euphemisms means that a euphemism, say coke, or a target keyword, say heroin, could be used in either the informative sense or the uninformative sense, as shown in the table. So therefore, the word to act, which learns all the embeddings of all contexts altogether, fails to distinguish the differences between the informative context and the uninformative context. The third challenge is how can we measure the similarities in the contextualized word embedding. So to solve the three challenges, we have proposed a new algorithm with three stages. First, to extract the contextual information. Then we do a filtering. We want to filter out all the uninformative context. And then lastly, we generate euphemism candidates. So by the first step, we do the contextualized information extraction. Then we will have all the available context information related to the target keywords. In this case, all the drug-related contexts. However, some of them may be noisy, as we have seen previously. Some contexts are too general, and they may bring in noise. So our second step is to filter out those generic and uninformative contexts. The last step is to generate the euphemisms based on the filtered context information. So let us look at the details of each step. The first step is easy. We will simply take all the sentences where any of the target keywords appear, and then we will remove the target keywords to form a masked sentence. The entire collection of the masked sentences contains all the information related to the drug in the given corpus. However, we find the collection may contain some noise. Therefore, the second step is to filter those uninformative masked sentences. So to solve this problem, we utilize a masked language model proposed in BERT. A masked language model aims to find the suitable replacement of the masked token. We empirically observe that if the masked sentence is specific to drug, then some target keywords will appear at the front of the replacement output. Otherwise, the replacement output will simply be some random words. Therefore, we set a threshold based on the validation dataset and remove those uninformative masked sentences. So now we have a pool of informative masked sentences, and we will generate euphemisms from there again. So right now, one more time, we are using the masked language model, since we already know that a masked language model can find the replacement of the masked token. Now we will use all the informative masked sentences, feed them into the trained masked language model, and the output, excluding all those target keywords, are the final output of the detection euphemisms. So to clarify, we have used the masked language model twice, once for filtering the uninformative masked sentences, the other one at the second time for generating the euphemisms at the third step. So let us move on to the results. As I have mentioned previously, the technique is generally applicable to multiple domains and datasets. We have experimented our algorithm on 3 datasets, including drug, weapons, and sexuality. All the 3 categories and datasets are cyber environment related categories, in which people tend to create involving euphemisms. And also to note, all the datasets are real datasets from social media platforms, such as Reddit, Gab, Twitter, and some underground discussion forums. The output of the algorithm is a ranked list, where the more confident candidates appear at the front of the list. So we use the precedent k as the evaluation metric, which is to see how many of them are correct of the first k detection results. So all the results are summarized on the right. The green correct tick marked our results, and it clearly outperforms all the baselines by a significant margin. So besides this quantitative analysis, we also perform our qualitative analysis, and we show that our proposed algorithm can even find some correct euphemisms that are not even on the ground truth list. So this also suggests the rapid evolving nature of the euphemisms and the necessity of an automatic euphemism detection algorithm. So we have already shown that our algorithm for detecting the euphemisms. However, without understanding what a euphemism is, we are still one step behind of the content moderation. So the next necessary step is to understand what the euphemism means by identifying which word that the euphemism refers to exactly. So let us see again of the problem formulation. This time, we need the input of a text corpus and a euphemism. We would like to output a probability distribution of the target keywords it refers to. Take weed as an example. We expect the probability of marijuana is highest. Take coke as another example. We expect the probability of cocaine is the largest. So the task of euphemism identification is considerably challenging. So to the best of our knowledge, no prior work has successfully achieved this task. The technical challenge lies in twofold. The first is the resource challenge. The second is the linguistic challenge. As of the resource challenge, since it is an entirely new task, we have no available datasets, and also it is even unclear what kind of resources we need. As of the linguistic challenge, we find the target keywords. The differences between the target keywords are often very subtle. It is hard to capture of them. And for any of the euphemism, say coke, they can be either used in the euphemism sense, which is the drug sense, or the non-euphemistic sense, which is the beverage sense, which adding an extra layer of the linguistic challenge. So then we propose to use two of the techniques to solve each of the challenge. We propose to use the self-supervised learning to tackle the resource challenge, and we propose to use the coarse to fine-grained classification algorithm to solve the linguistic challenge. So first, let us see how it is possible to curate a dataset by self-supervised learning. So we extract all the sentences that exclude the target keywords, the marijuana, heroin, ecstasy, and so on, mask the target keywords. Now we consider the masked sentences as training example, and the target keywords as labels. So then this will naturally form a new dataset, where the inputs are those masked sentences, and the respective labels are these target keywords. By learning from such a dataset, we can already form a multi-class classifier to determine which target keywords this masked sentence refers to. So how about the linguistic challenge? How do we want to enlarge the subtle differences between euphemisms? Now we have seen a euphemism coke could be either used in the euphemistic sense or the non-euphemistic sense. Then how do you know which sense it is using, and how do we remove them? Now we construct another coarse classifier to make the decision. The goal of such a classifier is to distinguish whether the masked sentence is using in the euphemistic sense or not. So we construct a pool of positive examples and negative examples. So to obtain the positive instances, we just use all the sentences on the left. And for the negative sentences, we adopt a negative sampling approach. We randomly chose a sentence in the corpus and randomly mask a sentence, and we consider that as a negative example. So right now we have two classifiers. One classifier is the multi-class classification to know which drug, which target keyword it refers to. Another one is to see whether the masked sentences is drug related or not. So let's have an overview of the model. Take weed as an example. We aim to generate a probability distribution where marijuana is highest. Assume we already have a trained coarse classifier and a trained fine-grained classifier. We first extract all the masked sentences that contain weed from the text corpus, and then using the coarse classifier, we filter out the masked sentences that are not related to drug, and then we will use the filtered masked sentences as input to the fine-grained multi-class classifier, and obtain the target keywords labels for each of the master sentences. So say now we have 45,000 marijuana labels and 5,000 ecstasy labels. And then the final output of weight is just a probability distribution by the number of labels for each target keywords. So to summarize, we have tackled the resource challenge by a self-supervised algorithm that can curate the dataset by itself. So besides the linguistic challenge are solved by a coarse to fine-grained classification scheme. Such hierarchical architecture enlarges the differences between the target keywords and has shown better discriminative performance. So since there's no previous work for such a task, we compare our approach with a few simple baselines and evaluation studies. We evaluate our algorithm based on the accuracy at k, which is to see whether the correct answer is in the top k precision or not. We show that our algorithm outperforms our crafted evaluation studies baselines by a large margin. We refer the readers to the paper for more details on the baselines. Okay, thank you very much for watching. Make sure to check out our paper and the open source code at the GitHub link so that you can detect euphemisms on your own datasets.